So this is the final solution of the MVDR method. I could have given you this solution right away, but I thought that this Lagrange multiplier scheme is very powerful technique, and it can come to your help unexpectedly. And it is good for you to understand at least the basic stepwise process by which you can apply this Lagrange multiplier based constraint optimization method. It requires some mastery of the rules of derivations and all that, but if you have even a tabular summary of those derivative rules, even if you don't understand where they came from, you can apply this MVDR method and it will give you, you can apply this Lagrange multiplier technique and it will give you the optimal answer, optimal result. Okay, so that was a little bit of a kind of a segue. We kind of went into this Lagrange multiplier technique a little bit, but we are now back to the main topic, which is the formulation of this MVDR method. Okay, Arushi, you have something to say?
No, sir. That was regarding the session only, the interactive session only.
Okay. Okay, fine. So now let us look at the some of the consequences of such type of filter. Remember, initially our power spectral density was based on the simple filter Wn of f. These are the DFT filters. The MVDR method says that we can do better than DFT. Essentially, we take the DFT filter and multiply by RXX inverse. So then what do we get by doing that? Oh, by the way, yes, the MVDR scheme in terms of block diagram is same as the method of DFT. We are still formulating a parallel bank of this WF of n, but each W of F on F of n we are multiplying by RXX inverse. So it is still a bank of bandpass filters. And then the output of the filter still would be denoted as Y of n. We would take expected value of Y of n magnitude squared. And then that way we will determine the frequencies of arrival. Okay, so let us look at some of the consequences of this MVDR technique. Let us consider first a simple case where there is only one complex exponential signal present, which we are denoting by Wn of f. And there is this vector S. Actually, the symbol S. This S is now a scalar. If I multiply the MVDR आपको क्वेश्चन क्या है? लेकिन आप मुझे क्वेश्चन पूछे वो मेरे पहुंच में नहीं आ मैं ये बता रहा हूँ लेकिन का रजिस्ट्रेशन है वो मैं कंट्रोल नहीं कर पाता। रजिस्ट्रेशन का कंट्रोलर नहीं है, इसके लिए आपको पीसी का पीसी का नहीं मिल सकता तो, लेकिन फाइनल डिसीजन पीसी का नहीं है। हाँ हाँ, तो इसको आप पीसी का नहीं से बात कीजिए। तो मैं okay. So sorry for the interrupt. Um, um, what I wanted to say here is that if the incoming signal has the frequency for which this MVDR has been designed, then you will see that the output signal actually corresponds to the symbol of interest, which means that the MVDR actually has done what we had asked it to do. At the signal of interest, WF of n, it gave a gain of unity, and that's why we directly got S back. It didn't attenuate S. It didn't amplify it also, but it didn't attenuate it either. The reason is because of that constraint that we had, that our filter at this frequency should have unit gain, and that is why this S got multiplied by just 1. If you wanted it to amplify this signal, then we could have said that constraint Wn Hermitian Wnf, instead of 1, we could have made it 10. Then this S would be 10 times S. The point of this sequence of equations is to show that MVDR has done what we asked it to do. At the correct frequency, the MVDR filter passes the signal without any attenuation or without any amplification, essentially without any distortion. In other words, the terminology D here is proven by this equation here. You may say that, fine, we don't want to attenuate the signal at that frequency, but we would actually like to amplify the signal, because then our signal will get stronger. In fact, it doesn't matter. We don't want to amplify it, because if we amplify the signal here, the noise also will get amplified coming into the filter. And so in terms of the actual quality at the output of the filter, we would not gain anything. And so to keep to avoid getting into that distraction, we have said that the filter output at that frequency should be just unity gain, which as seen here, the MVDR does that. Okay, and then the MVDR output corresponding to the noise component also we can determine in the manner similar to the equation on the last slide, and it turns out to be this, where U is the vector of the noise sample. And if we want, we can actually calculate the variance of the noise at the output of the filter. It takes this particular formulation. Let's not get into that right now. This is not as important or as critical as of now. But what is probably more important is to look at what is happening to the magnitude, expected value of the magnitude squared of the output itself. We want to know what is the expected value of Yn magnitude squared, because remember that is what was that was giving us in the case of the DFT filters, it was giving us the power spectrum, and even with the MVDR, we are ultimately going to just take the expected value of the output of these different filters for different values of small f, and then we are going to take the maximum of those outputs and say that that is where the frequencies are present. So just the way that we did these two equations, for the MVDR, we can also calculate expected value of Yn squared magnitude. Now, Yn is given as Wn Hermitian Xn, and if I substitute the expression for Wn, which is beta times Wfn Hermitian Rxx inverse times Wfn, and then I take expected value of Yn and magnitude Yn squared, we get this particular expression here. Can anyone tell me where this expression in the first line came from? Komal, can you explain where this first line came from? Yes, you have anything to comment, Komal?
that is WNRX, the WN herniation RX into
You are
W.
barely audible. Maybe you need to
Hello.
come closer to your microphone.
Hello.
Yes.
That is WNF herniation into RSH into WNF. That
Yes.
term.
Yes. You're right. I think you're right. I didn't fully understand what you're saying, but I'll take your answer. So recall that I'll move all the way back. Recall that we have already formulated the expression for expected value of yn squared magnitude squared. Expected value of magnitude of yn squared. We have derived it here on slide number 22. All that I'm doing is instead of Wf of n, I'm substituting the expression for the MVDR filter that we got. That is the only change that I made. The reason I'm spending a little more time on this is because now for the MVDR case, with that I am getting a very specific answer, which is what I am showing over here. The first line came from that slide number 23, and then the rest of the lines are just simple simplifications of the first line. Essentially, it turns out that this expected value of magnitude of yn square is given by this expression here. So compare this with the expected value of magnitude of yn square for our earlier scheme, the power spectral density scheme. There it was just this expression that we have seen on that slide number 23. So compared to the original expression, somehow the MVDR did something similar. It is still computing this type of Rayleigh factor in some sense, but there are two changes. One, this term which was in the numerator, it went into the denominator, and this matrix, correlation matrix, became the inverse of the correlation matrix. Okay, fine. So let us move forward and summarize the MVDR technique. I think I'll have to stop in another 5 minutes. But just bear with me. I think we ended up spending a lot of time inefficiently today. Okay, so in the MVDR based frequency of arrival estimation scheme, we estimate the correlation matrix using some number of incoming signal samples. Just like the DFT based scheme, we take some large number of equispace frequency points, and then for each value of f, we determine this MVDR pseudo spectrum, which is given like this, which was on the previous slide. And then we plot the MVDR spectrum as a function of f, and the frequency of arrivals are located as the peaks of this MVDR spectrum. Okay, so that is the summary of the MVDR technique. Okay, so remember on this slide, we said that the alternative techniques are music algorithm and the MVDR algorithm. And then the third algorithm is this expectation maximization algorithm. So let us get to this expectation maximization later on Wednesday. But before we conclude today, let us look at the comparative performance of the standard DFT based estimation of power spectral density the music and the MVDR. Okay, so we will do that now. So if today's lecture was not inefficient, I would have covered this expectation maximization technique today itself. But that I am not able to do now. But at least still, let us compare side by side these first three techniques. And here, what I have done is I have taken N to be 12. The number of transmitters I have taken to be 10. So there are 10 simultaneous sources. And in each of these cases, remember, we are evaluating the spectrum. And for that evaluation, I am taking 1,000 points in this range. Okay, so let us see the results. This is my regular power spectral density that I formed using the DFT technique. This red circles here are the locations at which these 10 transmitters are transmitting. So this is the frequencies of arrival, which we are trying to estimate. And this is showing the match filter output. The match filter is the original DFT scheme. And you see that, yeah, fine, the DFT scheme does tell us where these locations are. At each of these locations, the DFT does give us some type of a peak. By the way, this vertical lines, I have drawn it to coincide with the frequency. So at each of these vertical lines, this DFT spectrum kind of registers some type of peak. And then everywhere else, it kind of goes down. So in a way, this mesh filter scheme is doing what it is supposed to do. But these peaks are kind of flat. If there is some noise, we will easily mistake this negative 0.38 to be maybe negative 0.35 or maybe negative 0.42 or some number like that. The noise can easily kind of shift us from this peak, because each of these little things are kind of like the, as I was saying, they have low resolution. They are like the tip of our finger. Contrast that with the MVDR. Do you see the difference here? At each of these locations now I have a needle, a very sharp needle. MVDR is telling us unambiguously what the frequencies are. And now if there is noise, the noise will have to be so much stronger for us to say that negative 0.38 is negative 0.35. At negative 0.35, the MVDR is all the way like negative 30 dB below the peak. So the noise will have to be 30 dB stronger for us to make this point stronger than the actual peak. Whereas for the DFT technique, the noise has to be maybe less than 1 dB stronger than the actual location. So MVDR, you can see, is clearly performing much better. It is almost giving us those direct delta spikes, direct delta function impulses. The music algorithm is even slightly better than MVDR. It is giving us even more localized spikes. Right? So this is the magic of mathematics. If you say that, okay, fine, these figures look impressive and they seem to have done the job, they seem to have solved the problem, I want to tell you that it is not just these figures. There are multi-million-dollar projects whose fate, whose engineering fate depended on whether we can just do this blue match filter type of curve, or whether we can do either the red or the yellow NVIDIA or the music type of curve. And if the mathematics was not there, if some ingenious people would not have figured out a way to get this type of, sorry, once again, just hold, this will be very short. Okay, so this is where we will end today. Uh, Basically, some elegant mathematics has been used in a very innovative manner to solve a problem which was, even the mesh filter solves the problem in a very nice manner, in a very intuitively satisfying manner. But the limitations of the mesh filter are clearly removed by the NVIDIA and the music technique. And so this is, today where I'm ending this lecture is where I would kind of strike a note regarding the research, that this NVIDIA, the music, they came out of the research works of research scholars like you. And there were problems which were identified, and after identifying the problems, the solutions were developed in a very fundamental manner, in a mathematically ingenious manner. And that provided such a very drastic and visually impressive performance gain in terms of in this particular application, the estimation of frequency of arrival. Okay, so next week when we come, we will be looking at this compressive sensing based viewpoint of frequency of arrival technique. And that will lead us to this expectation maximization algorithm. And the reason I'm bringing this to focus is because this EM algorithm, similar to possibly this NVIDIA algorithm, but maybe a little bit wider in the scope, is a very powerful technique. And those of you who are maybe interested in the general domain of machine learning, where this EM algorithm kind of comes up every now and then. Maybe not as much as the deep neural networks these days, but still it is one of the techniques which is extremely powerful. And so, although we will be looking at the EM algorithm in the context of this FOA problem, once we understand the basic concept of the EM algorithm, that will kind of empower us to apply the same concept, the iterative concept of the EM, to again a wide variety of problems which have nothing to do with FOA. That is going to be the content of our Wednesday lecture. Okay, so we'll stop here.